So we have seen the ionic bond from the perspective of Lewis structure, in which one atom gives its electrons to the other atom, and we form an attraction between those oppositely charged ions that occur. We've seen covalent bonding, in which one atom and the other atom share their electrons, okay? So that's a covalent bond. So we've looked at those two things. We're going to kind of take a little break from drawing Lewis structures practice, and we're going to learn eventually how to draw those Lewis structures that I left you with in the last lesson. But we need to define something called electronegativity before we proceed much further, and here is why, all right? We know that an ionic bond is formed by the transfer of an electron. You transfer the electrons and exchange the electron from the metal to the non-metal, and that forms an ionic bond. We know that a covalent bond is by sharing two electrons, or maybe more, between atoms, okay? If there is equal sharing between those two, we call it a pure covalent bond, or, and we'll call it more commonly, a non-polar covalent bond. There is equal sharing between the two atoms. But there is a world in between those two levels. There is a sharing that is unequal, okay? And when the sharing is unequal, we call that a polar covalent bond. So we need to look at this continuum right here. They're not, all either ionic or all covalent. Back in our early days of learning ionic compounds and covalent compounds, we had a kind of a hard and fast distinction. We said ionics occur between metals and nonmetals, covalent occur between nonmetals and nonmetals, and there was no knowledge of anything in between those two. There is something in between those two, and it's called a polar covalent bond. Okay, why is it called polar covalent? In our image on the screen, what we have here is what we a electron distribution graph, in which where it's red when it's real electron rich, and it's more blue when it's electron poor. Okay, what this is actually a image of HF. Now, if I were to do the Lewis structure of HF, and I will do it for you here, it has one electron being shared. But those electrons being shared are not being shared equally. Fluorine has a higher attraction of those two electrons than hydrogen does. Now, I'll tell you why that is later, but for now I'm just telling you that it is. And those electrons are not being shared equally and are spending more time at fluorine's house. And so that is what we call a partial negative charge. And where the hydrogen is being left a little bit high and dry and not getting to share those two electrons equally, has a partially positive charge. Now, we know this happens because when you put these things into a magnetic or an electric field and turn those on, all the molecules are going to align with the polar plates. So the negative end will all align with the positive plate, and the positive ends will all align with the negative plate. So we see this, this alignment that occurs. So this is a property that these guys have. If it were equal sharing, we would not see this happen. And we know that it does happen, so we know that the sharing is unequal. So this transition from metals and nonmetals are ionic, and over here, when you share completely equally, it's covalent, or we call it nonpolar covalent. There is this middle ground where there is kind of sharing, but it's not very equal sharing. So what's happening there? You got those two electrons, and you might have drawn them as being shared, but they spend a little more time over here than they do over here. So there are times for a brief moment that this is actually negatively charged and this is positively charged for that brief moment. And so overall, we just say it's negatively partially charged over here and positively partially charged over here. So this is a continuum. As we look at elements on the periodic table, if they're really far apart on the periodic table, then they're going to definitely have this ionic character. They're not sharing. If they're really close, maybe even the same atom, they're going to be sharing perfectly equally. But as they get closer and closer, it's kind of sharing but not equal sharing. And it's getting better and better, and they're sharing better and better, and now it's really equal sharing. So it's a continuum across the board. There's no sharp distinction. There really isn't between ionic and covalent. It is no hard and fast, this is the line. But we do define it, and we come up with a way of saying, let's say since this is mostly ionic, let's call them ionic. Since this is mostly sharing, we'll call it covalent, and then we'll talk about that middle ground. Okay, we have to define something called electronegativity. Electronegativity helps us put it into one of these three categories. Is it ionic, is it polar covalent, or is it covalent? Okay, and electronegativity is a discussion about how those electrons are being shared, and let's define it. It is not an energy, okay? It is a tendency. It's the ability of an atom to attract towards itself very specific electrons. Those electrons are the shared electrons, okay? The electrons of the, I shouldn't call them shared, the electrons involved in bonding. The ability of an atom to attract towards itself the electrons of a chemical bond. All right? So what we have is values placed upon these. Scientists came up with, they did a lot of comparisons between these two electrons. This guy's got a higher ability than this. Pair these two electrons, these two atoms, this one's got a higher ability than this. So they were able to do all kinds of comparisons and come up with numerical values to rank them by their values. So these are just relative values that were assigned to each atom based upon how they behave when they form bonds. Now, if we look at this table, it's kind of a nice table. It's showing by the height of the element its electronegativity value. It also has the values on there, but you can easily see what the trend is. As you move across the periodic table, you're going to see that it's getting bigger as you go to the right, and it's getting bigger as you go to the top. I don't want you to memorize any of those numbers that are on this table, but I do want you to know the trend. Electronegativity increases as you move to the right on the periodic table, and it increases as you move up the periodic table. Examine that periodic table for just a moment and tell me what elements are being left out of that periodic table. Well, it's the noble gases, isn't it? We don't have helium, neon, argon over there on the right-hand side. Why is that? Well, if you think back to the definition, and let's go back to the definition, okay, of electronegativity. The ability of an atom to attract towards itself the electrons in a chemical bond. We don't have chemical bonding with those noble gases. Some of them don't do it at all, and the other ones do it very, very rarely. So that is what's being left off of this periodic table, because they do not have a tendency to attract electrons in a chemical bond because they don't have a tendency to form bonds. So the most highly electronegative atom is our fluorine. Fluorine is the biggest bully in terms of wanting to snatch electrons. He wants those electrons to get the noble gas configuration, has a stronger ability to do that than any of the other elements on the periodic table. This matches our metallic character as well. On the bottom left are the guys who do not want to attract electrons, okay? And they have the highest metallic character. And on the top right are the ones that have the strongest ability to attract electrons. They have the least metallic character. Okay, so we're not going to memorize the values, but we're going to make sure we know that trend and that the noble gases don't have values associated with it. Now, once we have that information, then we can do something with it. We have to know the cutoffs, okay? So we look at elements and we come up with what we call an electronegativity difference. We take the two atoms in the bond, so we're looking at the bonds, we're looking at the elements in the bond, and we're comparing their numbers. And if that difference is very small, we say that that is a covalent bond, okay? That would be from 0 to 0.04. We just call it a pure covalent bond. Now, it's only truly pure, equal, complete sharing when the difference is 0. But if it's down to 0.4, we'll call it covalent. If we're in the intermediate range of 0.4 up to 2, then we call that a polar covalent bond. And if it's bigger than 2, then we'll say, okay, it is so different that that would get the ranking of ionic. Now, the first thing that I want to note to you is this value 2. This textbook uses 2. We'll use 2. I have taught from other textbooks that use the value of 1.8. So this is not even a hard line for this, but we'll use the 2 line. So what this is saying is in this range, they're sharing, but not sharing very equally, and the more electronegative atom will have the more electronegative value. So here we have equal sharing, okay? Here we have unequal sharing occurring, where you have a partial negative and a partial positive. And here, the sharing is so unequal that the electron is spending so much time over at the other guy's house, it's fully negative, a full negative charge with a full positive charge, and that is the ionic bond. So we can look at values, and we could come up with actual values for for which kind of bond do we have. So let's determine if these are polar, covalent, or ionic, or covalent. Okay, so ionic, polar, covalent, or covalent. Let's at least do it in the order we see here. How would we do that? Well, the first thing that we would have to do is we would have to come up with the numerical values for the electronegativities of those atoms. Now, see that it has a subscript of 2? Know that we don't have do anything with the electronegativities like double it. We're just considering the bond between barium and chlorine. This connection between these two. Is it ionic? Is it polar covalent, or is it covalent? Well, it's a metal and it's a non-metal. And in the past, that's all we looked at. We said, okay, metal, non-metal, ionic. Well, let's see if the numbers play out that way for us. So I'm going to have to go back to our periodic table here so I can look up some numbers. Where's barium? Barium is right here, and it has an electronegativity of 0.9. And chlorine is right here. It has a value of 3.0. So we can say, all right, barium is 0.9. Chlorine was 4.0. Let's do a subtraction here on the screen. 4.0 minus 0, I'm sorry, I said 4.0, but it's not 4.0. It is 3.0. All right, so we have the 3.0 minus the 0.9, and what does that give us? That gives us a 2.1. Now that is greater than 2, so yes, this is an ionic bond. Okay, now let's go to the next one. The next one we want to do is carbon monoxide. All right, so when we did carbon monoxide, we were considering the connection between those two, and we cannot consider the connection between those two. I mean, if we didn't consider values, we'd say non-metal, non-metal, that's covalent. Was it polar covalent or regular covalent? We didn't have that language before, but we would have considered it covalent because it's a non-metal to a non-metal. But let's go back to our periodic table of electronegativity values. And let's look these values up. Carbon is right here and oxygen is right here. So carbon is 2.5 and oxygen is 3.5. So 3.5, just take the big number minus the small number. It doesn't matter what order you're doing it in. We're looking for the positive value there. That is an electronegativity difference of 1. And we know that electronegativity difference less than 2 or greater than 0.4 is polar covalent. So we would think, all right, they're sharing, but they're not sharing equally. See if we have another one or not. You're going to do this one. Go back to that table and look up the values for aluminum and chlorine. All right. I want to know, you got aluminum chlorine, you're looking at the compound AlCl3, and you're looking at the compound O2. Got 2 different compounds. I have 4 answers there that you're going to choose from once you look up the electronegativity differences. Okay, what did you come up with? Did you come up with this actually being polar covalent for the aluminum chloride, but the oxygen was a pure covalent? We wouldn't use the word polar with it. Now that is surprising maybe at first, because if you don't look up the numbers and you look at this and you say, hey, that guy is a metal, and that guy is a non-metal, And always when we took a metal with a nonmetal in the past, we've always said that that was ionic. But these electronegativity differences are actually less than 2.0, so this is a polar covalent bond. O2 is as pure as a covalent bond as you can get. You're going to have a 3.5 minus a 3.5, and you have the equalest sharing you can get. Electronegativity difference of 0, that is going to be a pure covalent bond. Last thing that I want to mention is something called a dipole moment. A dipole moment is a numerical representation of how polar a molecule is. Okay, it's abbreviated with that mu. You see that mu there? That's the symbol for it. And you will never have to calculate a value for it, but it has something to do with the charge separation and the distance between that charge separation. That's R, okay? Now what you do need to know as a connection is just general trends. As the difference in electronegativity increases, the dipole moment is going to increase. Now these are all diatomic molecules. Once you start getting a molecule that's got more than 2 atoms, it gets a lot more complicated, and we will talk about that in future chapters. But right now they're all diatomic. Here we have electronegativity difference of 0. Every time the electronegativity difference is 0, it has a 0 dipole moment. That's the only one that I expect you to assign a value to. But we do see the trend. Here the electronegativity difference is getting bigger and bigger as we go down, okay? It's getting larger. And that we can determine by taking and subtracting those values. So we know that this one is ionic. This is polar covalent, and this is a polar covalent as well. And this is just a pure covalent. Okay? As it gets more and more difference in electronegativity, the dipole moment is also getting larger. So we see that trend. I expect you to know that trend, and that is a numerical measure. It actually has a unit for it. A debye is what it's called, I think. It's got a unit for it, so there's a numerical measurement for that value. It is actually measurable by putting this thing into a chamber and see how much electricity, charged plates it takes to get these things to align well. So it's actually a measurable value. You will never have to assign a value to it. You should be able to assign a value to electronegativity differences. You should be able to classify things as ionic, polar covalent, or pure covalent based upon electronegativity differences. You ought to know the trend between dipole moment and electronegativity differences, but you won't have to calculate a dipole moment.